All right, welcome to this video for Chem 161, where we'll be looking at some of the impacts or results of applying intermolecular forces on materials and thinking specifically about boiling points and the energy it takes to vaporize a quantity of material. Okay, so we'll take a look at this chart here to guide our conversation. And we'll start here with understanding each kind of column in the table. So we have the substance listed below. We have something called methane, ethane, normal butane, normal pentane. And right next to it, we have the formula. Okay, so we see here that the formula indicates that we have a CH4 molecule. So in Lewis structure, we're looking at this molecule. In ethane, we've extended that by one carbon, so we can think of the central features of the molecule as being a C-C single bond, and then we populate the remaining spots around it with the necessary amount of hydrogens to completely satisfy octets at carbon and duets at hydrogen. So there's ethane. Butane is the C4 version of this, so we're going to see a chain of 4 carbons, and again, top and bottom hydrogens all the way around, and termini of hydrogens to that chain. And pentane is the C5 version. So you could imagine that the C6 version could exist, the C7 version could exist in it, and that is in fact a series. So all of these compounds, methane, ethane, butane, pentane, these are from the class of compounds called alkanes, a term that one would learn in more detail in organic chemistry. Okay, regardless, we have some information set up to understand boiling point, BP, and we see here that the units expected there are degrees C, okay? So this is the temperature at which the compound, pure compound, starts to boil, okay? If we had water listed here, we would expect 100 degrees C listed for the boiling point for water. Okay. The next column is the enthalpy of vaporization. Okay, so we've seen enthalpy before. That typically refers to energy. So here's energy units, kilojoules. So I'm recognizing that. And this is per mole. So what this is the energy it takes to vaporize 1 mole of the compound. Okay, so if I had 6.022 times 10 to the 23 molecules of methane, we could list here the energy it takes to transition that from liquid to gas. Okay, so that's the energy to vaporize 1 mole of the compound. And we'll have entries for each of the methane, ethane, butane, and pentane molecules down the column here. Okay, so what we want to do with this table is, at this point, see if we can address a couple of questions. Okay, so I invite you to pause the video and try to answer the following question. Which molecule has the lowest boiling point? And what we want to think about is the weakest intermolecular forces. So use what you know from the formula and the Lewis structure for methane, ethane, etc. to try to predict the strength of intermolecular forces as they might go from high to low or low to high according to the structure of the compound. Okay. When you have an idea for which has the lowest boiling point, resume the video and let's see if you are right. Okay, so hopefully you were reminded of London dispersion forces, LDF, and how the length or the contact area that a molecule can make with twin molecules nearby is our predictor for how strong the intermolecular forces due to London dispersion forces, how high they may be. Okay, so here I see a very small carbon chain. I see a medium carbon chain, a longer carbon chain, and probably the longest in this series would be the C5 equivalent. Okay, so it goes that as we go down the columns in this table, that we are increasing the length of the alkane molecules from methane to ethane to butane to pentane. So perhaps this is another moment where you can pause the video and answer, if you weren't able to before, on which would have the weakest intermolecular forces and therefore the lowest temperature needed to boil the compound. Okay, so hopefully you are thinking that the smallest molecule, methane, with just one carbon, would be one that has the least contact surface area between neighboring molecules. If I have a longer ethane molecule, two of these, they would have an increased opportunity to contact one another and establish London dispersion forces like we learned about earlier. Butane, even longer, so the London dispersion forces are going to be stronger and are going to attract butane molecules to one another even further, even more effectively than ethane. And likewise, pentane, even longer. So I would expect methane to have the lowest value for the boiling point there. And I'd expect the highest to be the pentane. Okay. Good. So those are boiling point thoughts. And we can move on and ask the question, which might have the highest enthalpy of vaporization? So recall, this is the energy required to break intermolecular bonds in the liquid. Okay. So here we want to say which one is going to have the highest requirement for energy to break 1 mole of intermolecular forces between molecules. Again, take a moment to see if you can predict the answer on this, and we'll move forward. Okay, so answering this question, highest enthalpy of vaporization, hopefully thoughts on boiling point were helping you here, and I would expect that the highest intermolecular forces due to London dispersion forces aligning with the highest boiling point would lead to the highest energy requirement to vaporize 1 mole of the compound that is pentane. And I would expect this to be the lowest. Okay. So with that, let's take a look at the actual data. And so here, I'll just make some room for some of those answers so that we can read that nice and clearly. And in fact, our thoughts there were correct. It looks like the lowest boiling point is methane at minus 162 degrees C, and that pentane boils at about 36 degrees, 1 degree C, which is about body temperature. So that is, if you held with the right glove, held pentane in your hand that was at your body temperature, this would boil right in your hand. Now, the energy required to vaporize 1 mole of the material is listed here in a kilojoule per mole value, and you can see here that the values increase as we extend the chain, that is the alkane chain, down the series from methane to pentane. Okay, so again, we've emphasized here that as attractive forces go up, this is to say that as the intermolecular forces due to London dispersion forces, in this case, go up, with the increase in the size, we're seeing a trend in the boiling point. Okay. Now remember, increase in size is speaking to the polarizability, the sloshiness of the electron clouds that are bonding all elements together in the molecule. Okay. Good. So you can actually look at the results in that series the same way. So here's the methane molecule, CH4. Here's the ethane molecule, C2H6, etc. And you can see here that as we go from the C1 to the C2 to the C3 and all the way up to the C 1, 1, 2, 3, C8 molecule here, that we are able to see a nice uniform trend in the boiling point as a function of the molar mass of that compound. Okay, so molar mass is another way to describe the increasing length as we add units down that chain. So recall, as the pattern we had was two termini of CH3, and what was extended in the middle was something that can be extended. So I'm going to put in the middle here, we have a CH2 with a value of X. And X here is allowed to be 0 for ethane, or X can be 1 for propane, or X can be 2 for butane, or X can be 3 for pentane, etc. Okay, and we would expect, because of the increasing formula for the compound, that the molecular weight of that compound should increase. Okay, so boiling points do in fact track with the molar mass in this series that is showing a simple extension of the carbon chain to a longer value. Okay, let's push ourselves further and think about perhaps an even simpler class of compounds, but one that you haven't necessarily thought about before. Let's think about the noble gases. So the noble gases are listed here. Again, you would find these in group 8 of the periodic table, last column at right in the periodic table. Helium, neon, argon, krypton, and xenon, down the column here of noble gases. Okay. The atomic mass, again, values extracted right from the periodic table listed to only one decimal point is listed right beside it. And we just saw how this might be analogous to the molecular mass of the alkane series on the previous slide. You can see here that as we go down the column, that in fact the molar mass is increasing. And you'll recall our conversations about atomic size. We know that as you go down a column in the periodic table, atomic size is increasing as well. So we can look at the table and look at the same categories, boiling point and the enthalpy of vaporization, energy to vaporize 1 mole of the noble gas. And so again, we can ask very similar questions. Which gas is going to have the smallest London dispersion attraction forces? So here's a moment where you can pause the video and circle the element that you would expect to have the smallest LDF values from the series helium through xenon. Resume the video when you've got your answer. Okay, so hopefully you realize that helium was very small and that xenon was the largest element here from our series. And that if we're making the argument based on contact points, that the higher surface area large xenon atom is going to have greater contact point, greater polarizability, greater sloshiness of the electron cloud that establishes the size of the atom. And that's going to allow xenon-xenon intermolecular forces to be highest, and therefore helium-helium London dispersion forces to be the lowest. Okay. And then highest down here. And hopefully your appreciation for the energy it takes to vaporize 1 mole of the compound is kind of aligning with what you might better understand as boiling point. This time listed in degree Kelvin. So note that. And we'll show the kind of next question. Which gas might have the highest boiling point? So we've deduced here that the xenon should have the highest boiling point given the higher surface area of the larger xenon atom. And we can also equate that to the high enthalpy of vaporization expected here. Okay. So let's take a look at the data and see what we have. So we have in degree K, 4 degrees Kelvin to boil helium, and all the way up here at 165 degrees K to boil xenon. And in terms of the energy required to vaporize a mole of those materials, here we're dealing with very small values compared to the previous numbers, okay? And that is because we have very weak intermolecular forces between these noble gases, but still measurable, and we see the numbers increase down the series. Okay, so again, we're seeing how the attractive forces between atoms, in this case, noble gas atoms, are increasing with the size of the feature in question, in this case, a noble gas atom. Okay, and last but not least, we'll take a look at this series. So here's ethane, butane, and decane now, all the way to 10. So remind yourself of what you predicted for the boil point and enthalpy of vaporization in that series, and compare that across to another class of compounds, not the alkanes this time, but this time the alcohol version, where the terminus of the molecule is replaced with an OH group. This is called the alcohol group. And you'll notice that it has an OH. So in the first series, we know that there are intermolecular forces that are London dispersion forces. We expect London dispersion forces in the second series as well, but there's going to be an additional intermolecular force. Please list this for yourself and resume the video when you've got that. Yeah, we are talking about the FON feature, oxygen bonded to a hydrogen. So we're talking about the hydrogen bond. Okay, the hydrogen bond, as you recall, is the strongest intermolecular force that we have, and it's going to tether alcohol molecules to other alcohol molecules stronger than those without it. So as we answer similar questions about boil point, we already knew that boil point should increase as we extend the alkane chain, and consequently the enthalpy of vaporization should go up as well. And this is a moment where you might try to predict whether or not the values in the red column here would be higher or lower than the similar cousin molecules ethanol rather than ethane, butanol rather than butane, and decanol rather than decane. So try to predict if you would expect larger values in the right set of data than the left set of data, and resume the video when you're ready. Yes, that's right. So hopefully you were able to predict that given our ability to hydrogen bond with this group, that we should see a significant increase in the intermolecular forces. So much stronger IMFs expected here due to the hydrogen bond present that is programmed by the presence of the alcohol group OH in these series. Okay, so we'll notice the boil point of ethane increases dramatically from minus 90 all the way up to almost 40 almost up to 80 degrees C. Butane, a boiling point close to that of turning ice into water, and in this case it boils at a temperature just above that of boiling water, 117 degrees C. And decane boils at 174 C, and this time almost 60 degrees hotter than that still. Okay, and again, our enthalpy of vaporization increases and tracks with the boil point. Okay, so we've used intermolecular forces, focusing initially on London dispersion forces, and then use that to predict boiling point trends in the alkane series, and then we've evolved that to a similar series that are the alcohol compounds shown here, and we've recognized a hydrogen bonding group, the OH group here, that is found at the terminus in these molecules, and we've been able to rationalize a stronger IMF as a function of the presence of that OH terminus on these molecules, and we've predicted higher boil points that is actually reflected in the data. Okay, so I hope this has been useful for you in showing how our tools for predicting structure and polarity and can ultimately be used to predict properties of